Hi everyone. Today I will be introducing our work of linking convolutional kernel size to generalization bias in phase analysis synthesis. This is a joint work by Rice University, Yale University, and University of Houston. Today I'll be introducing our work from four parts: background and motivation, framework, experiments and results, and finally the conclusion. For the background and motivation, typically when people are talking about a model, to say whether they're bad or good, they focus more on the accuracy of the model. For example, if a model has 10% accuracy higher than another, we say that this model is better. And recently, people started to focus on the fairness of the model. That is to say, for the same model, if we find that this model perform much better on a specific group than another, for example, in this figure, it performs much better on the children group and the more senior people. We see that there is a fairness problem of the model. And when talking about the bias and fairness of the model, classically people focus on the dataset. For example, do they have equal number of samples? And how about the diversity of the dataset? And also they focus on the image qualities of the dataset. And in our work, we hypothesize that the model's architectural design is also going to influence the model's fairness. For example, the activation functions and also the convolutional kernel size and also the depth and the width. In this paper, we focus on the convolutional kernel size. And from the other angle, we know that there are high-frequency biases in the neural networks. The model will perceive both high-frequency components as well as the semantic ones, leading to some generalization behaviors counterintuitive to humans. That is because when a model is making a decision, they pick up both high-frequency information and semantic information, while the humans only picks up the semantic information while ignoring the high-frequency information because it's too hard for people to tell them. And in the previous work by Caro et al. In 2021, they found that there are the local convolutions can cause an implicit bias, and especially for those models with a smaller kernel size, smaller convolutional kernel size, that more easily to focus on the high frequency part of the image. And next, I will introduce our framework. Our framework consists of three parts. First, we perturb all the test images with out-of-distribution perturbations. In this work, we use adversarial attack perturbation and frequency noise injection perturbation to make a new test dataset which contains the same images but with different noises injected. I will talk more about the OD perturbations in the experiments part. And next, we send the new test images to different models where the models share most of the architectural design, but differs only in some small part. For example, convolutional kernel size here in our paper. And last, we collect all the results got from the second step and split them into different groups according to the sensitive attributes and apply our causal analysis on the results. And now I will talk about the experiments and the results. We vary out the first layer kernel size. We vary the first layer kernel size from 3 to 5, 7, 11, and 13 over ResNet 34. We also test our framework on ResNet 50 and ResNet 101. And we also varied all the convolutional kernel size, and we got similar results. We use gender as the target attribute, meaning we're doing a gender classification, and then we use race as a sensitive attribute. We train all the models on fair face and unique face dataset, and we use FGSM and CW adversarial attack introduced in the second step. For the first results, we visualize the perturbation spectrum. We first do the adversarial attack to all the original test images, and we collect all the adversarial perturbations and visualize the average spectrum by race and kernel size. And here are the results. Each row here represents a model with a different first layer kernel size. And we find that as the first layer kernel size increases, the spectra become more concentrated at low frequencies. And the spectra for the black risk group consistently have less energy at high frequencies compared to the spectra of the other risk groups. Male spectra also have lower high frequency information compared to to the female spectra. These results demonstrate that changes to first layer kernel size induce different feature biases for networks, which also vary by protected attribute subgroups. And we also have the frequency noise injection perturbation experiment. Our goal with this perturbation is jitter all frequencies with the same magnitude in an input image. To do this, we inject random noises to the Fourier coefficients of an image lying on an annulus of a particular radius in the Fourier spectrum, according to a specific expression. And then we apply the inverse DFT on the images to get the original images back with the noises. And here are the results. We show models' performances with different first layer kernel size for Black and Indian here separately, and in each individual figure, the x-axis here is the frequency we're injecting energy at, and the y-axis here is the accuracy of different models. It is obvious that all the models suffer from low to mid frequencies energy injections and become robust to mid to high frequency noises. It is hard to directly tell which group is getting more influenced than the others, which further asks for a quantitative analysis. Due to the time limit, I will not introduce the causal analysis theoretical part here, but here are some results. Those coefficients tell that how different models are reacting to different groups separately, and the coefficients here for the Black, we can tell that it's always higher than those of the other race groups. And in addition, the coefficients values for different frequencies within the same race group are also significantly different. As a conclusion, we find that smaller convolutional kernel sizes can cause NCN to be biased towards high frequency features, and increasing the kernel size mitigates this bias. Such frequency bias significantly differ across different race and gender subgroups, and we find that all the models trained on the two datasets focus less on the high frequency features for the Black and male subgroup.